Hi everyone. In this hands-on session, we'll use Shap framework and try to understand the fraud detection model which was built in our earlier session. So this hands-on session has 4 different sections. First, develop the model. Second, generate the Shap values. Third, we do a local interpretation. And fourth, we do a global interpretation. Now, the first section, develop a model, it involves loading the essential libraries, loading the train and test data, perform feature engineering and develop the model. This has been extensively covered in the previous section. So, I am directly jumping into the second section, which is generating Shap values. In order to generate the Shap values, we must first install the Shap library, which can be done by pip install Shap. Once the Shap library is installed, we can import the Shap library into our dev environment. Now, a quick recap on the details of the model and the training data set. So, the model which we have used is a decision tree classifier under the variable CLF. The train data which we have used is final X train, and the essential features that go into the train data are amount, city population, age, transaction month, distance, merchant, category, gender, state and job. So, for our simplicity, especially for local interpretation, I have considered 3 records. Record number 2449 is actually a fraud record where the model has predicted the specific record to be a fraud, and I have 2 other records which are not fraud. One is record number 2 and the other is record number 678. Going further, when we want to explain a fraud or a non-fraud record, we will use one of these record numbers for our simple explanation. Once the Shap library is loaded to our dev environment, we have to create an explainer object. And our model is a decision tree classifier. Hence, out of the various Shap explainer objects, we are selecting a tree explainer. So, the tree explainer has 4 different inputs which need to be loaded. The first is model. Model denotes the actual model which we are trying to explain. In our case, we have defined the model as CLF, and hence we are entering model CLF into the argument. While initializing this object, we are excluding the data, and hence we are mentioned that data is none. The explainer object will require the model output data type. So, right now we are considering the model output to be raw. There are other options like probability which can also be used by the explainer object. Finally, the feature perturbation. The tree path dependent is one of the feature perturbation method, and that's the default option provided when we go for a no data initialization. Once the explainer object is created, we can generate the Shap values by using the Shap underscore values method. The input for the Shap values method is the actual data set. Here we are using the train data set for generating the Shap values. Below we see a quick summary of the shape of the data set. Currently we are considering 300,000 records from the train data set, and you can see that there are 300,000 records in the initial data set shared, and we also have Shap values for all these 300,000 records generated. So, before jumping into the interpretations, let's first try to understand how Shap is able to explain model's prediction or model's output. So, in order to understand the model's prediction, Shap uses 3 major features. One is called the base value. The base value is nothing but the mean value of all the predictions that have been done on the training data set. This can be compared to the $50 profit margin in our earlier example, where we haven't introduced any product, and this is the base value or the base margin that is recorded without introducing any feature. Then we have the model predicted value. Model predicted value is the final output. This can be compared to the $83 profit margin which is obtained after introducing all the 3 products in our earlier example. And here model predicted value is nothing but the actual outcome of a model for a particular record. The third one is Shap value contribution, which can be either positive or negative. This is nothing but the marginal contribution of each and every product. In our example, we saw debit card and credit card had a negative impact, whereas UPI had a positive impact. So this can be explained by the block diagram below. On the left, we see that the base rate is 0.1, which is the value, or which is the expected value of the model when there is no feature involved. And on the left, we see the feature values for one single record. Here there is 4 features considered. And finally, we have the output, which is 0.4. So this explains that the model from its base rate 0.1 has deviated and moved to a point which is 0.4. Shap will try to explain how this value or how each individual feature has contributed in such a way that the base rate has been changed from its initial value, which is 0.1, to the final predicted value, which is 0.4. And during this explanation, it will show these positive interactions or positive contribution with the color red, and any negative contribution is indicated by blue. Let's jump on to local interpretation. Local interpretation explains the model's prediction for every individual record. This will explain how each feature has contributed for the model's outcome. There are different plots by which we can visualize the local interpretation. We'll first start with the waterfall chart. So waterfall chart tries to give a step-by-step manner in explaining how the model has predicted the value from its base rate. Now first let's compare the fraud data which is 2449, and in order to generate the waterfall chart, we need to enter the base value, the essential Shap values, the feature columns or the feature names, and finally we need to also enter the max features that need to be displayed. In this section, we see that the base value is 0.007. This is the base value that is recorded for our model CLF, and for this particular record the output predicted value was 1. And this waterfall chart gives the detail on how each individual feature has contributed to this deviation from 0.7 to 1. And this has been also sorted out in the order of highest impact. So we can see that amount has the highest impact, which is a positive 0.64 and indicated in red. Similarly, category and state follows the highest order. Let's move on to a record which is not fraud. So here we are considering record number 2, and as you can see in the waterfall chart below, the base value is 0.07, and this has been deviated based on individual contribution of the feature, and the final predicted output is 0, which means that it's a not fraud record. And we can also see here that the same list of features like amount, category, which had a positive impact in the previous record, has a negative impact here. So one basic underlying thing is, from both of these records we are able to understand that amount is one of the prime factors that is determining the model's prediction. Now let's jump on to the second type of visualization, which is called the force plot. The force plot provides a similar detail like the waterfall chart, where the positive contributions are denoted in red and negative contributions are denoted in blue. However, in this representation, we have all the specific features in single bar, double arrowhead, which is seen below. So we are considering the same fraud record, which is 2449, and the force plot uses a similar kind of input: the expected value, the Shap values, and the essential features. And here we can see the base value is 0.07 and the model predicted value is 1, and the individual contributions of each of this feature is mentioned here. Similarly, if we take a record which is not fraud, here we have considered record number 678, we can literally see how the base value 0.07 is modified or moved to 0, and also see the essential features that have contributed for this negative impact. Similarly, let's consider a record which is not fraud. Here we are considering record number 678, and we can see that the base value is 0.07 and the various features like category and amount has contributed negative impact, and this has pushed the value, the predicted value to 0. Now the important or interesting feature about the force plot is these force plots can be stacked together in order to give a better representation. So how do we stack them together? So these horizontal charts, when we take for a single record, can be flipped vertically and stacked for multiple records. Now let's try to create the force plot for 100 such records, the first 100 records. So what we see below is the force plot for first 100 records. On the x-axis we have all the 100 records stacked from 0 to 100, and the y-axis denote the model predicted value, and each individual record is nothing but the horizontal bar which is flipped vertically to give a better representation. And this force plot has is versatile because we are able to change both the x-axis and y-axis to understand the impact of features on the overall record. Now instead of understanding the Shap value of all the features and how this impacts on the model predicted value, let's say I want to investigate on how a particular feature like amount is affecting across these records. I can actually select amount effects and see how amount is creating a positive or negative impact. So right now this chart clearly indicates that for the first few records, around 7 records, we have a negative impact in amount, and whereas the remaining records have a positive impact on amount. Similarly, we can select for all the features that are for which the Shap values have been generated. Let's say if we select for age effects, we can see how age effects have been different for different section or different rows. Previously we analyzed how Shap value for individual feature is distributed across the records. We can also understand how Shap values are distributed across each individual feature. This can be done by altering or changing the x-axis. Now if we change the x-axis to age, we can see how the Shap value has been changed or how Shap values is recorded for different age groups. So this way we will be able to cross-examine the Shap values with respect to individual features. Let's move on to decision plot. So decision plot has the amalgamation of both waterfall chart as well as a force chart. In decision chart, we will have a similar representation. So the decision chart has amalgamation of both the waterfall chart and the force plot. In decision chart, we have the essential features that are plotted in the y-axis, and the x-axis denotes the model output value. And the use case which we have here is a non-fraud record, which is record number 2, and we can see the base value is 0.07 as indicated, and the line chart indicates how the specific feature has impacted the model base value and how the model is turned out from its base rate 0.06. So decision chart is another kind of visualization for local interpretation, and it has an amalgamation of the features from both waterfall chart and the force plot. So similar to the waterfall chart, we have the different features that are stacked in the y-axis. The x-axis denotes the model output value. So and the representation starts from the bottom where we have the base rate 0.07, and there is a line chart that travels across different features where the deviation corresponds to the contribution of each individual feature. And finally, we have the model output or the predicted value, which is 0. In this case, we are considering a non-fraud record, which is 2. Hence, we see that the base rate has changed from 0.07 to 0. Similarly, if we consider a record which is fraud, we can see that the base value starts from same 0.07, but each individual feature provides a positive or higher impact and has pushed the model predicted value to 1. So this is similar to the waterfall chart, where we can understand how each individual feature impacts the predicted value. Similar to the force plot, we can also understand or try to analyze group of observations in decision plot. So here we are trying to understand the first 100 observations, and each individual line here indicates single observation. So this chart provides that most of the records, almost maybe like around 80% of the records are 0, which is non-fraud, and there are few records which are fraud, and we can see how each individual feature is impacting the final predicted value. So let's move on to the global interpretation. In global interpretation, we'll first witness on the summary plot. So the first thing to be noticed with global interpretation is we are considering the entire training data set. Hence, all these plots will consider all the records that have been utilized by the model for prediction. Now the summary plot has multiple representations. First we'll focus on the dot representation. So the chart below is a dot representation chart, where the x-axis denotes the Shap values and the y-axis denotes the different features that are used by the model. And this chart is sorted to the order of highest impact. And we can see that amount has a larger impact, and the color code is this Shap value indication whether it is providing a positive or a negative impact. From this chart, it is clear that amount, category and age are the top 3 features that are influencing any decision, either to be a fraud or a not fraud category. The same summary chart can be also represented in a violin chart to have a better visualization. However, the entire x-axis, y-axis and the color codes remain the same across the summary plot. The third representation of summary plot is a bar chart. Here, instead of looking at individual Shap values, we have a collective or aggregated value, and the aggregation is nothing but a mean Shap value for individual feature. And this bar chart provides a better visualization in understanding the impact of individual feature. So we know that amount and age are one of the major factors that decide the model's outcome. However, in order to understand the contribution or the relative importance of each of these features, this bar chart provides a quantified way of representing how each feature impacts the final output. Next, we move on to the dependence plot. Dependence plot is a scatter plot which provides or gives insight on individual feature, as well as trying to understand the comparison between two features. Now let's take the dependence plot below. Here the y-axis denotes the Shap value corresponding to the x-axis which is a specific feature selected, and the color code of the Shap value is nothing but the closely related another feature. Dependence plot has the option of automatically selecting this feature. However, we can override and use a customization on top of this. On closely examining this chart, we are able to understand that any transaction that has a value greater than 2500 had a positive Shap value or a positive contribution, and this contribution is positively related to a feature which is category, which means that for these transactions that are greater than 2500, both amount and category had a positive contribution. So if we want to override the automatic selection of secondary feature, we can use the parameter called interaction index. By defining interaction index as none, we will get a dependence plot where there is only y-axis and x-axis for a single feature and there is no color coding. The below chart is a scatter plot of feature amount and its respective Shap values. So by using interaction index, we can override the automatic selection, and we can also do a customization of the secondary feature that needs to be added to the dependence plot. In previous section, we have used none to eliminate the secondary feature. Now we can use the same interaction index and try to introduce a secondary feature of our interest. Here we have used a for loop and try to plot 7 dependence plot And as we see here, category is one feature that has a close relation with respect to amount. However, when we compare other features, we have mixed positive and negative values. Hence, we will not be able to arrive at a particular conclusion or a specific interpretation. So in this hands-on, we were able to cover how a specific model which was created can be analyzed using Shap, and with local interpretation we were able to understand how individual feature play or contribute to the final predicted value, and through global interpretation we were able to understand how the model performs as a whole for the given training data set, and also to identify those important features that need to be considered for model selection or model validation.